Okay, we want to find the eigenvectors, eigenvalues of a matrix, the matrix being the matrix 3, 1, 4, 3. Okay, and to find the eigenvectors and eigenvalues for a matrix, we do something very similar to what we've done all along. An eigenvector is a vector that maps onto a multiple of itself. So, for example, in R2, if you have a transformation where two vectors, v1 and v2, map to multiples of themselves, that would be v1 maps onto lambda 1 v1, v2 maps onto lambda 2 v2. In R2, that might look something like this, where v1 is a vector here and v2 is a vector here. Okay, now, multiples of v1 consist of vectors that would start at that would have initial point at the origin and go to some point on the straight line through the v1 vector as we've got it here, so that v1 might map onto this vector, which is a vector along this line. Okay, and that would be your lambda 1 v1. What would lambda 1 be in this case? Well, let's see. It looks like you're multiplying v1 by a negative because this vector goes in the direction opposite v1. And it looks like it gets about 1, 2, 3 times as long. So maybe lambda 1 is negative 3? Question mark? Okay, so this might correspond to lambda 1 equals negative 3, and v1 is some vector whose y-coordinate is about half of its x-coordinate, or whose y-component is about half of its x-component. Okay, well v2 lies along this line, so any multiple of v2 is going to have to lie along this line. So if this is our multiple of v2 that we get from the transformation A, then it looks like, well, v2 is in the same direction, not the direction opposite v2. Sorry, lambda 2 v2 is in the same direction, not the opposite direction. And it looks like it's about maybe half as long. Okay, v1 here, maybe v1 from this picture is 2, 1. And v2, well, it looks like its y-coordinate is, what, about 4 or 5 times its x-coordinate, right? So v2 is what? Well, we could estimate it. Now, v1 has magnitude about 2, just a little over 2, so if that's 2, that's about double that, so the magnitude should be about 4, so it might well be negative 1, negative 4. It's not an unreasonable estimate. So that lambda 1 v1, if lambda is negative 3, would be negative 6, 3, negative 6, negative 3. And v2 would map to about 1/2 v2, so that would be like maybe negative 1/2, negative 2. Now, the whole dotted line here is the subspace spanned by v1. Okay, that would be this. And this line here, the line I've drawn through the image of v2, which is of course parallel to a line that I would draw through v2, would be subspace of R2 spanned by the vector v2. And the image of v1 is in the subspace of v1, the image of v2 is in the subspace of v2. v1 and v2 are clearly linearly independent. You should be able to see that geometrically. No multiple except 0, no non-zero multiple of v1, well, any non-zero multiple of v1 would be a vector along this line. We couldn't add any multiple of v2 to that in order to get 0, because in order to get 0 from a multiple of v1, we have to have a vector that's in the direction of v1, opposite the direction of whatever it might be, and v2 is not in that direction. It can't possibly combine. So a c1 v1 plus a c2 v2 can only be 0 if c1 equals c2 equals 0. So v1 and v2 are linearly independent. Now I'm doing this fast. This is just a review of what I would hope people would come out of linear algebra with. I believe my A students did. Not sure about those who made less than A's. Some probably did, and some almost certainly won't remember it. Okay, well, you probably had a similar experience in your linear algebra class. Anyhow, the other thing we can say is that v1, v2, the set v1, v2 spans R2. Every vector in R2 can be written as a linear combination of v1 and v2. Now you should understand all this language and what it's telling you, and also how it extends into higher dimensions in order to have a context for understanding what's going to come out of the analysis that we're about to do. Okay, well, in any case, we can find eigenvectors corresponding to this matrix. Just take the determinant of the A minus lambda I vector, you get your characteristic equation, you get your eigenvalues, you plug them in. Well, the A minus lambda I vector times your x1, x2 should equal the 0 vector. You plug in your lambda, and you get, for lambda equals 1, you get this equation that gives you x2 equals negative 2x1. And that's very similar to what we've been doing, so I'm confident everybody understands that. This is actually a little simpler because we don't have an e to the lambda t to multiply by our x1, x2 vector. The context here is a little bit different. For lambda equals 5, well, you do the same thing. And you get this eigenvector for lambda equals 1, this eigenvector for lambda equals 5. Now, if this was a system of equations, differential equations, you do an e to the lambda 1, well, e to the t times this, and an e to the 5t times this to get your fundamental set. But that's not what we're doing. I'm just kind of relating that and explaining why I'm doing this quickly, because it's the same thing you've been doing, but actually simpler. Okay. Well, now we do our t vector. Okay, and our t vector and its inverse are going to give us what's called a similarity transformation, and we'll talk about that in a minute. But our t vector is just, our t matrix, I'm sorry, is a matrix whose columns are these eigenvectors. So we take our 1, negative 2, and put it in the first column, our 1, 2, put it in the second column. And then we write down t inverse. Now, if it's a 3 by 3 or bigger matrix, you're probably going to have to do some row reduction to get your inverse. But I assume everybody can do that, and I will feel free to give you 3 by 3, maybe even some 4 by 4 matrices when I do a test. But to illustrate the process, a 2 by 2 matrix is sufficient. So we get the inverse of our t matrix. For 2 by 2, that's easy. We flip the one diagonal and make the other diagonal its negative. And we get this. And then we want to find the matrix T inverse AT, and things will start to become clear. You'll see at least part of what we're into here. This is a similarity transformation. Hopefully you know what that is from your linear algebra, but it's been 18 months and you might have forgotten, and you might not have had time to cover it in all the detail that would persist in your memory. It's time now to understand what a similarity transformation is, though.